Yeah, it's that you have a big system which is in microeconomical equilibrium. Side which there is a system, subsystem which is in canonical equilibrium. And we saw that for this system, the phase space density is to the minus bit. Let me use a new notation.
Sir, excuse me, sir.
Yeah.
Sir, you are not audible. Like echo is coming, sir.
Not audible. Who is coming? Now it is better or what? Maybe you have to mute yourself.
Yes, sir. Now it is clear, sir.
Okay. Okay, so this is the phase space density. Let's say it is a function of NVT. And if you take log and if you multiply that minus PPT, you get the Helmholtz free energy of the system that we saw has the expression 2 minus 3s. So you may ask, what is this internal energy? How do I compute this internal energy? So this internal energy by definition is the average energy. So then what you have to do, this h times e to the minus beta h eq. Equation divided by z. Because U by definition is the average energy, which is nothing but.
Sir, excuse me, sir.
Yeah.
Sir, when you're writing in the board, the voice is not clear, sir. The volume is very low.
Why is it that? You are saying that now the volume is very low.
Now it is okay, sir.
But if I say like this, it is low.
Now it is fine, sir.
Okay, so maybe I have to shout. Probably. Okay. Fine. Yeah, so as I was saying that this is the equilibrium density and this is the free energy. And if I want to know the internal energy of the system, that is the average energy, which is this guy. And if I use this expression in here, I get this expression. But as you can see, this is nothing but okay, what is beta? Beta is 1 by kVt. But then if I look at this expression, I see that this is nothing but minus del beta of log of the partition function. Because if I take the partition function, remember the partition function has this formula, the minus beta h of p comma q dp dq. So if I take the log of it and then take the derivative, I get 1 over z. And then if I take the derivative with respect to beta, I get minus h. That's why there's a minus h here. So this is the formula. And this, of course, you can write in terms of the free energy also. Okay. So this is easy. The next thing is to ask for the energy fluctuation. Okay, so how do you get the entropy? Entropy is, see, entropy is F is equal to U minus Ts. Therefore, Tf will be equal to Du minus Tts minus SdT. But this term is zero because in canonical equilibrium, the system has a constant temperature. So S is equal to minus, sorry, del F del S. Minus Ts minus SdT. Now I can use the first law of sorry, the second law of thermodynamics. So this is minus Pdv minus SdT. So therefore S is equal to minus del F del T and P is equal to minus del F del T. So therefore, once I know the free energy of the system, then I can compute everything, the internal energy, the entropy, the pressure, etc. Okay. So one more thing we need to look at, which is the energy fluctuation. We found out that the average energy, this is U, this is minus del beta of log of Z. But you may ask, what is the fluctuation in the energy? That is, what is the standard deviation? H square average minus H average square. How does it look like? This has an important consequence. So let's see, how does it look like? You see that you take this one and you take the derivative with respect to beta. You take the derivative of this guy with respect to beta, you get two terms. The first term is minus dpdq h square dpdq divided by this factor. Then you also need to take the derivative with respect to the derivative of the denominator. So that will give you, so it is 1 over z, so minus 1 by z square. So you will get square of the denominator. Now we have to take the derivative of this guy with respect to beta. So you get minus h. So this factor will remain, of course. Minus h, so that minus will make it plus. So you get this. But this quantity is nothing, the first quantity is nothing but by definition the average of the square of the Hamiltonian, and this quantity is the square of the average. just use this H average is this by this, so there's a factor of 2, so you get. So therefore we got the answer that this is equal to minus of del U del beta. Once I have that, you can rewrite it slightly differently. Get an important relationship, which is the following. So this minus del U del beta but beta is equal to 1 by kVt. So therefore this one is nothing but kVt square del U del t. Because dv beta is minus 1 by kVt square dt. This quantity del U del t is nothing but the heat capacity of the system. And volume. Why constant volume? Because U is a function of NVT. So therefore, we got an important relation that H square average minus H average square is equal to CB times KVT square. Where CB is this guy, heat capacity at constant volume. Now T is an intensive quantity. T is the temperature that doesn't depend on the number of particles. While CB is what? CB is del U del T. And since we are dealing with short range interacting system where every particle interacts with a finite number of other particles contained in a small region, so therefore Q is proportional to the number of particles. So CB is proportional to the number of particles. So CB is proportional to the number of particles. H average is also proportional to the number of particles. If I combine these two, then I find this relationship that the energy fluctuation, relative energy fluctuation, okay, so this guy goes as, the denominator goes as square root of n, the numerator goes as square root of n and the denominator goes as n. So this one will be proportional to 1 by square root of n, which is much smaller than 1. Why? Because we are dealing with a very large number of particles. So therefore, we get a very interesting result, which is the following, that in the microcanonical ensemble, energy was a constant of motion. Energy doesn't change as a function of time. In the canonical ensemble, of course, energy changes as a function of time, but the average energy is given by this is the average energy. It is given by this formula. This is the average energy. But what we find is that about that average energy, so if I look at the plot of the energy as a function of time, fluctuate, of course. This is the average value, which is given by H average. But above this average, this fluctuation, the relative fluctuation is very, very small. Very, very small relative fluctuations. So in the limit n going to infinity, you can neglect this fluctuation because it's a very small quantity that becomes even smaller if you increase the number of particles. So therefore, in the limit in which n goes to infinity, you may think of the energy of the system as effectively a constant. And now we can see how we can relate the microcanonical and the canonical ensemble. So in the microcanonical ensemble, the microcanonical ensemble, energy was constant, equal to some value, let's say T. In the canonical, energy not a constant, but very small fluctuations. Now what I can do, and these fluctuations, they are negligible, very much smaller than 1. Negligible in the limit n going to infinity. So therefore, the energy I can take this here to be constant almost. And then what I can do is that I can tune T, the temperature in the canonical ensemble. So this I call canonical ensemble, this is the microcanonical ensemble. I can tune my temperature because in the canonical ensemble, T is the tuning parameter. T is something that I can change because T is the temperature of the system, which is a constant. So therefore, I can change it by keeping it in contact with a different reservoir or heat pump. So tune my temperature in canonical ensemble so that the average energy in the canonical ensemble becomes equal to the actual energy in the microcanonical ensemble. So this is what is known as equivalence of ensemble or ensemble equivalence. Which is a great thing because it tells you that no matter whether you are dealing with, you're doing the calculation within a canonical ensemble or within a microcanonical ensemble, you are going to get the same answer in the limit, in the thermodynamic limit. That is in the limit in which you have very many particles contained in a very large volume. Large meaning much larger than the atomic volume. And in that case, there is no distinction as such effectively between the microcanonical description and the canonical description. Recall that in doing this derivation, we have used the fact that the system is short-range interaction. So if the system has long-range interaction, then this ensemble equivalent doesn't work. Then it's a different story altogether. While for short-range systems, this is what you get. Okay. So are there questions on canonical ensemble before I move on? Yeah, so let me know if there are questions. Otherwise, I move on to the grand canonical ensemble.
No questions, sir.
Okay, so okay, now we move on to the grand canonical ensemble, which is version. The picture is the following, that I have a big system. This system is in micro-canonical equilibrium. A small part of it, which is allowed to exchange energy with the outside surroundings, that is in you know canonical equilibrium. Now we look at the situation where uh, this part can exchange both number of particles as well as energy with the external surroundings. Okay. So therefore, I have the usual conditions that n is equal to n1 plus n2, V is equal to V1 plus V2. And of course, the temperature here and there will be the same. Temperature will be the same everywhere. So this is microcanonical and this is canonical, this part. But now what I can do is I can ask, let me look at an even smaller part of this system. So let me call it, let me change my notation a little bit. Let me call this guy 1, this guy 2, this guy 3. So this 1 can exchange both particles and energy. So I have a big microcanonical ensemble. A subpart of it is in canonical equilibrium. The whole is in microcanonical equilibrium. A subpart is in canonical equilibrium. The subpart that exchanges energy with the external surroundings. Now I look at an even smaller part of 2, which I call 1, which can exchange both energy and particles with 2. And I ask, what is the phase space density of this guy? So I have this, but also in 1 and in 2, both can fluctuate. But both can change because 1 and 2 can exchange particle number between them. And 1 is much smaller than 2. So therefore I have the condition that N1 is much smaller than N2. Now I want to know what is this thing. Because that now if I want to know the phase space of system one, then it has the dimension 6n1 plus 1. There is one extra dimension now added. Why? Because system 1 can have particles whose number changes as a function of time. So therefore, there is an added axis in the phase space, namely the axis representing the particle number. So therefore, when I talk about phase space density, I have to talk about this guy, O1 of Q1, P1, N1. Because that Q1, P1 doesn't mean that there is only one particle, it just means that there are 6 N1 coordinates and momenta taken together. So this is this. So this, how do I get it? I know that whole of it is in canonical equilibrium. So therefore, I want to know the information about only a part. What do I do? What I do is that this guy will be proportional to, I look at the phase space density of the entire system, which will be rho of Q1, L1, P2, Q2, L2, integrate over all possible values of P2, Q2, and then I sum over all possible values of A2 with the constraint that the constraint is that N2 is equal to N minus N1. And V2 is equal to V minus V1. But what is this guy? This guy is what? This is the canonical ensemble or canonical equilibrium of 1 plus 2. So therefore, this quantity is nothing but e to the minus beta of h of 1 Q1 N1 plus h of 2 Q2 N2 divided by the partition function, which will of course be a function of n, v and t. So let's just substitute this formula here. If I substitute it, then of course the part that depends on P1, Q1 and 1 that I can pull out. So this will be to the minus beta of h of P1, Q1 and 1. This I can pull out. This is a constant, I can pull that out. And then I'm left with this guy. Is the h of P2, 2 N2. I have to have the constant in mind that N2 is nothing but N minus N1. For this guy, the way that I have written here with the summation and the integral, it is nothing but the partition function of system 2 with number of particles equal to N minus N1 and volume equal to V2. If I just substitute it here, what I get is one of P1, P1, and 1 to be equal to e to the minus beta h of P1 Q1 N1 times Z of N minus N1 P minus P1 comma T divided by Z of NP. Like to do is I would like to make a Taylor expansion here because I know that N1 is much smaller than N. N1 is much smaller than N, so I can do a Taylor expansion here and see what I get out of it. Okay. So let's just do that. Taylor expansion of this way. So the way to do the Taylor expansion is to first know that Z of NVT minus KBT log of this is nothing but the free energy, which means Z of NVT, I can write it as e to the power minus F by KBT. Therefore, this factor Z of N minus N1 T minus V1 T divided by Z of NVT that I can write as e to the power minus beta F of N minus N1 T minus V1 comma T divided by e to the minus beta F of NVT. Now we can do a Taylor expansion of this. If I do a Taylor expansion, so the leading term would be what? Beta F of N V minus V1 T. Okay, so that doesn't depend on the variables that I have on the left hand side, so that I can forget about. So therefore, this guy will be proportional to what? Would be proportional to e to the power minus beta to N1 with a plus sign of del F del N. I hope this is clear because when I do a Taylor expansion, the leading term will be e to the power minus beta F N V minus V1 T. So this doesn't depend on the variables that I have on the left hand side. So that's just a constant as far as the left hand side is concerned. So I can just forget about it. So I'm left with the term e to the minus beta minus N1. So minus minus makes it plus, and the derivative of F with respect to N. But what is this thing? So this, let us just recall what is this. So we have to just recall the first law and the second law of thermodynamics for the case in which particle number is not conserved. Particles, can go back and forth and increase and decrease in number and so on. So the first law of thermodynamics, if you recall, was E cross Q equal to du plus PdV. And the second law says TdS is equal to du plus PdV. But these are the cases when the particle number is not changing. If the particle number changes, then you get an extra contribution, which is you get this term minus mu dn minus mu dn. But this mu is what is known as the chemical potential. So what is the utility of this? The utility is that if I want to know if I know is u minus ts, so ts is equal to du minus t ds minus s dt. But du minus t ds is minus pdv plus mu dn. Therefore, we get from here that del f del n is mu, the chemical potential. So this quantity therefore is mu, the chemical potential. And when the system is in equilibrium, canonical equilibrium, every part of it has got the same chemical potential. So therefore, when a system is in equilibrium, every part of it has the same temperature, same pressure, as well as same chemical potential. Okay, so therefore we got our answer. If I now plug it in here, what I get is this factor is nothing but e to the beta mu n1. Sorry, this was a proportional. Okay. Then we need to normalize it. I mean, the treatment is exactly identical to what we did for the sorry, canonical ensemble. Nothing new as such. For the canonical ensemble, what we did was we took the whole system to be in microcanonical and a part to be in canonical. And the way we obtain the canonical equilibrium density is by taking the microcanonical density of the whole system and integrate out the extra degrees of freedom subject to constraints. And then we got the canonical equilibrium for the subsystem to get the microcanonical this is what we call the grand canonical equilibrium. What we do is that we take the canonical equilibrium and look at a subpart of it that can exchange energy and particles with the rest. And this is the phase space density that we got. Of course, this has to be normalized. So if you normalize it, the normalization condition will now write as over T1 TQ1 of rho1 P1 Q1 N1. But then we have to also sum over N1. This should be equal. So this gives one the the grand canonical equilibrium density to be equal to e to the power beta mu n1 minus beta h of p1 q1 n1 divided by Q of mu Bt. So this is the normalization constant. This is what? This is just summation over n1 0 to infinity into the beta mu n1 p1 q1 to the minus beta h of p1 q1 n1. But this guy in here is nothing but the canonical partition function. So therefore, we get several interesting results. So so I get this result, then that when a system is in canonical equilibrium and a part of it is exchanging particles and energy with the rest, the phase field density of that part is equal to e to the beta mu n minus beta h divided by the partition function. And this partition function is nothing but summation over n going from 0 to infinity to the beta mu n times the canonical partition function. This is what we got here. What the questions? Let me pause for 5 minutes and see if you have questions.
No questions, sir.
So now that we have discussed this ensemble phase space density, let's look at the average number of particles. Just as in the canonical ensemble, the energy was not a constant, it was fluctuating, and we looked at the average energy and the fluctuation. Similarly, in the grand canonical ensemble, by the way, this is what is known as the grand canonical ensemble. So here it makes sense to look at the average number of particles. So let's look at that quantity now. If you want that I have to do this and multiply by 2 dqn, and then I do dp dq summation over n. This is the average number. Okay. So if I substitute it here, substitute that formula here, what I get is summation over n equal n dp dq to the beta mu n minus beta h divided by q n, sorry, q of mu b. I see that this formula is nothing but nothing but I have to take the delta mu dt log of mu b. Why? Because q mu bt has this expression. This is the expression for q mu bt. So if I take the derivative with respect to beta mu, I get an n factor, which is exactly what I have here. Okay, have to take the logs. If I take the log, this factor comes in the denominator, and then when I take the derivative, I get exactly the factor that I get. So this formula is similar to what we had for the average energy in the canonical ensemble. Something very similar is happening here. But now let us look at the n square average minus n average. The average, the change in the average energy. Okay, so to do that, to go back to some notes in thermodynamics. we had for the definition of the free energy was this way, U minus Ts. But this was the case when the particle number was a constant, when the particle number did not change as a function of time. If the particle number does change as a function of time, so then we have to change the definition and the free energy that I should consider is U minus Ts plus PV. This is what is known as the Gibbs free energy. We will see that for the grand canonical ensemble, this is the right free energy to look at. We will see, but let's see first, I mean, what do we get from the thermodynamics? So we have this definition for the Gibbs free energy. So if you do dg, then you get to du minus Tds minus STT right, plus PdV plus VdV. But the second law tells me that TPS is equal to PU plus PdV minus mu dn. So therefore, PU minus TPS plus PdV, PU minus TPS plus PdV, this will give me is equal to minus STT plus VdP minus plus mu d. Derive a number of interesting properties for this Gibbs free energy by considering the following thing. Recall that your okay, so let me just write it down here. This is my PG, where G was U minus Ts plus PV. Recall that our free energy from the microcanonical description, we know that our free energy is a function of S and V and N. Why? Because in the microcanonical ensemble, we know that entropy is a function of N and V and E. And within the microcanonical ensemble, E is equal to U, so inverting it, I get this. But these quantities, S and V and N, they are all extensive quantities. That is, they are quantities that are proportional to the number of particles in the system. V I know is proportional because V is what? V is equal to N is equal to rho. The density is equal to N by V. So therefore V is equal to N by rho. So it is proportional to N. N is of course proportional to N. And the entropy is also proportional to N. Why? Simply because S is nothing but kV log gamma. And gamma, it is exponential in the system size. Exponential in the number of particles because the number of microstates that are accessible to the system that grows exponentially with the system size. So therefore, when you take the log, you get S also to be proportional to N. And U itself is also proportional to N, the number of particles. So therefore, the following thing has to be true. That if I multiply S by some factor alpha, V by some factor alpha, and N by some factor alpha, then whatever I get is alpha times SBN. Why? Because everything is proportional to the number of particles. So it has to be true this way. So now what I do is that I differentiate both sides with respect to alpha. So what do you get? You differentiate both sides with respect to alpha, you get U from that side. u, sorry, from this side u, that would be equal to del u of alpha is alpha v alpha n del of alpha s d alpha s d alpha. I'm just differentiating everything with respect to alpha. Plus del of u alpha is alpha v alpha n divided by del of alpha v d alpha v d alpha plus del of u alpha is alpha v alpha n divided by del of alpha n d alpha n d alpha. This is chain rule. What is this get? D alpha is D alpha. This will give you just S. And del U del S. What is del U del S? So we have 1 over T that is equal to del S del E. And E is equal to U, which implies del U del S is T. So the first term is going to give you T. Similarly, this one will give me V. And I know that del S del V is P by T. I know del S del P is P by T and del S del U is 1 over T. So therefore this factor will just give me minus PV. You have to just substitute this. I mean, get rid of this thing here. And the last thing is what? Yeah. Now it should be okay, I think. It is okay, now?
Yes, sir.
Just keep it. This is what we get. U is equal to Ts minus PV plus d mu. So therefore, if I now do question that we get for U. But du, I know what it is. It is equal to so here Ts is equal to du plus PdV minus mu Dn. So du will be equal to du will be equal to TBS minus PdV plus mu Dn. And from this one, I get du is equal to PdS plus is PT minus PdV minus VdP plus N d mu plus mu Dn. So if I just compare two sides, what I get is Tt minus VdP plus N dV that is equal to 0. Recall that just 5 minutes ago we had shown that dg is equal to minus SPT plus VdP plus mu Dn. But I can use this expression to write STT minus VdP is minus NdV. So this is equal to ND mu plus mu Dn. That is to say this is nothing but dg is equal to mu n, dt mu n, which implies g is equal to mu n. So this is an important relationship. It says that the Gibbs free energy is nothing but the chemical potential multiplied by the total number of particles in the system. So now we come back to where we left off. Namely, we were interested in finding out the fluctuation in the number of particles within the grand canonical ensemble. So that we can do the calculation now. And let's see what do we get. So to do that, we have to take the following approach. Oh, we have the definition of the grand canonical partition function. If the log of this quantity I have to take the log of this guy, but what I assume is whatever, and this we will show later to be true, but we assume is just as in the canonical ensemble, the energy was large, is effectively constant. There were only very small fluctuations about the average. So here also we will assume the number to be effectively equal to the average number. So n is very much close to n average. There will only be very small fluctuations. We will show that indeed the fluctuations are very small. So therefore, in evaluating the sum here, I just replace n by the average number. So if I do that, then I get this to be approximately equal to log of e to the beta mu n average plus log of z of n average bt. What is this? This one is nothing but beta mu in average. And this we know I can write it in terms of the Helmholtz free energy. Because the Helmholtz free energy F is equal to minus kBT log Z. So therefore this is nothing but minus of beta of F of in average BT. So therefore when I take minus kBT log of Q mu BT, I get a minus mu in average here plus F of in average. But we already show what is mu n. Mu n is G, that gives free energy. So therefore, this one will be equal to minus of G plus F of in average BT. Now let us recall the definition of G. G was what? G was U minus Ts plus BP, and F is equal to U minus Ts. So therefore, G is nothing but F plus BP combined. So therefore, G minus F is PV. So therefore, this one is nothing but PV minus P. So therefore, I get a very important relation that PV is equal to KBT log of Q of mu BT. Therefore, we found a very interesting relationship, which is that whatever is the normalization constant, whenever I take the log of it and multiply it by either KB or KPT, I get something useful. For example, in the case of the microcanonical ensemble, the normalization constant was gamma. The normalization constant was the phase-space density. So that was gamma. So when I took the log of it and multiplied it by KB, I got the entropy. Similarly, in the canonical ensemble, the normalization was the canonical partition function. So when I took the log of it and multiplied by minus kBT, I got the Helmholtz free energy of the system. Similarly, in the grand canonical ensemble, the partition function is Q mu Pt. This was the partition function. When I took the log of it and multiplied it by kBT, I got the pressure times volume of the system. Okay. So this is an important thing, that whenever you have an ensemble and there is a normalization constant that normalizes the phase space density of the corresponding uh, ensemble, then what you have is, when you take the log of the normalization constant, you get something useful. And here we saw what is that useful quantity, that is the pressure times the volume of the system. So up till now, any questions? Because there is a small part that is left. Yeah. So there's one part which is good, but perhaps this I should do tomorrow, because today I covered a lot. So we talked about until now, so let's just summarize, because we have been doing this, so today is the third class. So what we did was, we started off with thermodynamics, okay? So we talked about the first law of thermodynamics and the second law of thermodynamics. To do that, we learned about the notion of work and heat. These are the two different ways in which you can transfer energy to a system. Either you do work on the system or you heat it up. These are the two ways. Then we found that the first law of thermodynamics tells you that the difference between the heat absorbed and the work done is a path independent quantity called the change in the internal energy of the system. Then we went to second law of thermodynamics, and the consequence of the second law that we discussed was the Clausius's inequality, that tells us that if you compute d cross q by t around the cyclic process, then this quantity is going to be either 0 or negative. It will be 0 if you are dealing with a reversible cyclic process. It would be negative if you are dealing with an irreversible cyclic process. Then we saw that we can use this Clausius's inequality to define a path-independent quantity, a state function, namely the entropy. And then we wrote down the second law of thermodynamics in terms of entropy. PdS is equal to du plus Pd. Then we said that, okay, we want to come up with a framework that would allow to relate entropy, internal energy, etc., in terms of the microscopic degrees of freedom, the coordinates and the velocities or the momentum of the particles constituting the system. So the way we went about doing that is to say that first we consider an isolated system for which the number and the volume and the energy, these are the three constants of motion. We saw that for a given macro state given by fixed values of the number of particles, the volume, and the energy, there are many different microstates, namely many different possible values of the coordinates and the momenta. And each possible set of values of coordinates and momenta defines a phase space point, a point in the 6n-dimensional phase space of the system. Then we found that there are many microstates, many phase space points that can be characterized in terms of a phase space density rho. And we derived the time evolution equation for rho, which was the Liouville equation. Then we said that it will so happen that at long times, the phase space density may become time independent. And if the phase space density becomes time independent, the average value of an observable also becomes time independent. So how does the phase space density become time independent? It becomes time independent when it Poisson commutes with the Hamiltonian. And one possible way to make it Poisson commute with Hamiltonian is to see that the phase space density is uniform, and that defines for us the microcanonical ensemble, namely an ensemble in which all possible microstates of the system are equally likely. The phase space density is uniform. Then in the microcanonical ensemble, we normalized the phase space density, we got a factor gamma, and when we took the log of it and multiplied it by Kb, we got the entropy of the system. Once we know the entropy of the system, we knew how to compute different intensive variables of the system. Temperature 1 by T is equal to del S del E, pressure P by T is equal to del S del V, and so on. Then we moved on to the setup today in which the system is in microcanonical ensemble, and we were interested in finding out the phase space density of a part of this big system, which is continuously exchanging like energy with the rest of the system. And this allowed to define what is known as the canonical ensemble, for which the phase space density is given by e to the minus beta h divided by the canonical partition function. The canonical partition function plays the role of the normalization constant. When we took the log of it and multiplied it by minus kBT, we got the Helmholtz free energy of the system. And again, when we take the derivative of the free energy with respect to either the number of particles or the volume or the temperature, we get a quantity that we know from thermodynamics, because we can combine everything into the framework of, fit everything into the framework of thermodynamics. The last thing that we did was we have a big system which is in canonical ensemble. Then we looked at a subpart of it, which is exchanging both energy and particles with the rest. And what is the phase space density of the subpart? We found out that that is given by the grand canonical ensemble, e to the beta mu n minus beta h divided by the partition function. This is the partition function. And again, when we took the log of it and multiplied by kBT, we got something interesting, physical, namely the pressure, the product of the pressure and the volume of the system. Okay, so I think it is a good point to perhaps stop. Yeah. So yeah, so are there questions that we can take up?
No questions, sir.
So then please read, Carson Wong or whatever book you have handy, and then we can take it up again next time, which is tomorrow morning. Okay?
Sir, book reference.
Book I told you, no, the book by Carson Wong. Today, yes, so yesterday the first lecture I told you the book to read from. It's a book by Carson Wong. Okay, so this is called statistical mechanics. It has an Indian edition also. And I have written a book with a student. So this is P. Das and S. Gupta. The book is called Physics of Noise. Published by Springer. So whatever I taught today and yesterday, they are all from my book. But please feel free to also read other books. For example, this is an excellent book, Carson. Okay.
Okay, sir.
Okay then. Thank you very much for your attention, and we meet again tomorrow. Okay then. Thank you.
Thank you, sir.
Thank you.